Right, in this lecture, we are going to design an IIR digital filter using impulse invariance transformation technique. In the previous class, we have discussed about the various steps involved in the design of IIR filter using both the transformation techniques like impulse invariance transformation technique and bilinear transformation technique. Now we'll use that design procedure to solve on a particular problem. So we'll solve this problem. I'll read out this problem first. So design a digital low pass Butterworth filter with a passband and stopband cutoff frequencies 200 Hz and 500 Hz respectively. The passband attenuation is minus dB and stopband attenuation is minus 12 dB. The sampling frequency is 5 kHz. Use impulse invariant transformation. So how to design this problem? Always the first step is write the given desired parameters to design your H of Z. So what are the given parameters? One is the alpha p. So passband attenuation is given as minus 5 dB and stopband attenuation alpha s is minus 12 dB. And what are the other parameters we have? We have a passband frequency fp is equal to 200 Hz and fs is equal to 500 Hz and sampling frequency fs is equal to 5000 Hz, right? So how to find out our digital angular frequency? So digital angular frequency from the standard formula we can write it as Wp is equal to 2 pi EFP by Fs, and that is, if you replace with the values, Fp is 200 Hz by 5000. This is 0.085 radians per second. The same way, omega s is equal to 2 pi EFP Fs by Fs, that is 2 pi into 500 by 5000. This is 0.025 radians per second. And from this you can plot the frequency response. Now I'll draw the frequency response for the given parameters. On x-axis we have digital angular frequency, that is omega, right? So the maximum value is 5, right? So from the problem, what they're asking, they have given 0.085 radians per second is your passband frequency. Means here I have an attenuation of how much? Minus 3 dB. And also you have stopband frequency, somewhere it is 0.25. So this is the required frequency response, and here we need to remember one point. Actually the maximum value is 5 and this side minus 5. Most of the times we'll take normalized value, means we'll divide the whole scale with 5. So in this case, so the normalized value we can take it like 0.08 radians per second, right? And this I can take like 0.2 radians per second. Right, obtaining our digital angular frequencies from the problem is, we can treat it as a first step. So what is the next one? From the problem I have my normalized digital angular frequency, that is passband frequency, angular frequency I got 0.08 and omega s is 0.2. Now to design, what is the second step? Actually, second step, I need to design my h of s. So to design h of s, I need analog angular frequencies. That is, I need omega p, how much, and omega s is equal to, right? I need to find out these two values. As we are using impulse invariant transformation technique, so from that there are transformation formulas. We need to use that formulas. What are the transformation formula from analog? That is the relation between digital angular frequency and analog angular frequency, which is given as, from the transformation, omega is equal to omega by t. This omega means digital angular frequency. From this, I can write my omega p is equal to omega p by t. The same way, omega s is equal to omega s by t. For simple calculations, let us assume t is equal to 1, right? So then what it is, omega p is equal to 0.08 and omega t is equal to 0.2, right? So now I got my omega s and omega p to design h of s, that is analog transfer function, right? So to find out our h of s, what we need the order of the required analog transfer function. So we need to compute n from the given parameters. What is the formula for n, right? You know that this is log root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 whole by log omega s by omega p. So if you substitute the values in the n, what we have root of 10 power 0.1 alpha s is 12 dB minus 1 by 10 power 0.1 alpha p is 5 dB minus 1 whole by log omega s. Omega s is 0.2 by 0.008. So this is my n. Then I'll compute, after calculating this, your n is equal to, actually n is greater than or equal to 1. This is 1.05. So if you take a nearest integer, this is equal to 2. So now the order of the analog transfer function is 2. As we discussed, we can easily compute the required transfer function for analog Butterworth filter using the formulas, and for n equal to 1 to 4, for order of up to order of 4, we can use the tabular form and you can directly use the transfer function. So from that, what is h of s for n equal to 2? You know that is 1 by s square plus root 2 s plus 1. But need to remember, this h of s is a normalized transfer function. Means here the h of s is given as omega c is equal to 1 radians per second. But for our problem, we have a omega c, a particular value. So we need to compute omega c, then we'll derive the h of s for this particular omega c. Right. So the next step is we need to find out omega c. So what is omega c formula? Omega c is equal to omega p by 10 power 0.1 alpha p minus 1 whole power 1 by 2n, and substitute the values. Omega p we know 0.08, and then this is 10 power 0.1 alpha p is this is 5 dB minus 1, you know from the form previous expression, like n is 2, so that is, so if you simplify this you will get a value 0.2073. So once you got the omega c, we need to find out desired transfer function. Desired means it has a particular omega c value 0.2073. We need to find out h of s for this value. So how to get it? As for the previous discussion, we need to replace s with s by the new omega c. If you substitute this, that is s by 0.2073, right? Now I'll substitute this s by omega c in my h of s. What is our h of s? H of s is actually 1 by s squared. S squared means this is 0.2073 whole square plus root 2 into s by 0.2073 plus 1. And after simplifying this expression, you will get h of s is equal to 0.043 by s square plus 0.293s plus 0.043. This is the desired analog transfer function, right? So but what we want h of z, right? So we want h of z, but how to get h of z from h of s? We have to use, because we are designing with impulse invariant transformation technique, we need to use the transformation formulas of impulse invariant transformation to transform h of s into h of z. Now, so what is the relation? So if you have any pole n minus s minus pk, right, the equivalent transformation in z transform is 1 by 1 minus e power pk. Pk is that particular pole in s plane into t is a sampling time, into z power minus 1. So now I have to write my h of s in terms of number of poles. How to write this? Actual h of s is, you have 0.0430 by s square plus 0.293s plus 0.0430. So we need to write this as in terms of 1 by s minus p1, some constant, plus some constant b by s minus p2. Once if you know the p1 and p2, I can find out the corresponding z transformation expressions, right? Now you can write h of s into two summations. If you use the partial fraction expansions, you will get 0.2264 j by s minus 0.1466 plus j 0.146 plus, actually this is minus this is one part minus, what you have is, if you use a partial fraction expansion, 0.2264 j by S minus 0.1466 minus J into 0.146, that is 66, right? Now if you convert into this form, I can transform my h of s into h of z using impulse invariant method. How to do this? So the first one is, actually if you observe, this is your P1, right, and this is your P2. Now I can write my h of z is what I can write, 1 by, that is 1 into the constant is 0.2264 j whole by 1 minus, what is your pk? Pk means here it is p1. P1 is minus 0.1466 plus j 0.1466 into t. What is t? T we already assumed it is 1, so make it 1, right? Into z power minus 1. In the same way, the second one is minus 0.2264j is a constant, and if you want h of z, right, we are writing h of z, right? This is h of s, we are writing h of z, right? So h of z is, this is n minus 1 minus e power, what we have, p2. P2 is here minus 0.1466 minus j 0.1466 into t is 1, minus, into z power minus 1. Now we'll simplify our h of z. So if you simplify the expression, h of z is equal to minus 0.0571 whole by 1 minus 1.7088 z power minus 1 plus 0.7459 z power minus 2. This is our desired h of z using impulse invariant transformation technique, right?